Okay, in this chapter, we're going to actually start learning how to create a schema. Okay. This is what we'll be studying is we're going to review some guidelines for good relations, and then we're going to get into what is a functional dependency and how to normalize our data so we actually have a well-formed database that is efficient, reduces the amount of data that's duplicated, and reduces the chance for some anomalies that could occur on our inserts, deletes, and updates to a database. Okay. One of the things I'm going to talk about first, though, is you actually are learning the basics of how to create a schema here. Not the next module, but the module after, we'll be creating ERDs like this. What we do this week and next week will be creating the tables or entities that we will then put into a diagram like this. In the class, I'm not going to have you write SQL for a create table statement, though, okay? Because this is fairly trivial compared to the mental work required to create this ERD, to create the relationships. Okay? Another thing, if you have an ERD created, you can simply forward engineer it, like I'm going to do here real quick. I'm just going to do a basic, oh my gosh, put that in. Hit next, and it actually creates the SQL necessary to create those tables and build the database. So that's one reason we're not covering create tables. Another reason we're not doing it is, as an application programmer, the chances of you writing a create table statement is very slim. That is normally a task assigned to a DBA. Right? As application programmers, we use the data, and we're going to focus the last half of the class on how we actually use the data that we have in a database. The objectives for the course say that, you should learn how to create a database, and that's what this week and the next 2 weeks we will be doing. We will be looking at data, putting it into tables, and then drawing a diagram. Okay, the first thing we're going to look at in this chapter are these informal design guidelines. And we're going to go ahead and talk about these. Okay. Really what we're looking for here is that we don't have those multi-valued or composite attributes, and that the semantics of a relation actually makes sense. Okay? Because we want to be able to explain our relation to people. Let me give you an example of that. Oh, wrong one. Let me get here. Okay. We have our company database schema. All right. In the employee table, I have first name, middle initial, last name, on and on and on. Now, I could have named the table R, and for the attributes, I could just have A, B, C, D all the way down. Okay. It would still be a valid relation. However, the semantics don't make any sense. Okay. What is attribute A? I don't know. If I see an attribute F name in the employee table, okay, I can pretty reasonably assume that's going to be a first name, right? But I have an attribute A in a table named R. I have no clue about the data that would be stored there. So we want to make sure that we have decent names. Okay? We also want to make sure that we get rid of multi-valued attributes. Okay? An example of that would have been the department table. If we were going to keep department locations in the department table, we would have to have a multi-valued attribute, because we have department 5 that has 3 locations. So we would have to have an attribute named location that basically stores an array within it with those location names. And we don't want either of those. We also don't want to have a many-to-many relationship, okay? Because that is impossible to implement in a relational database. And let me give you an example here of how the works on database came about. Let me just get a few pages in there and scroll back up. Okay, the works on database. Okay, it has Okay, the works on database, it's there because it is used to implement a many-to-many relationship, and that works on table or relation is actually what we call an associative entity, right? So let me go ahead and draw out what we're actually trying to model. Oh gosh, I got to get it on draw here. Okay, so we have employee table. There's our employee table, and we have our projects table. And we have what we call a many-to-many relationship. And in a couple of weeks, we'll learn more about these ERDs and what all these symbols mean. But for right now, it means that a project can be worked on by one or more employees, and an employee can work on one or more projects. Now, so SSN is our primary key and employee. P number is our primary key over in the projects table. So to have a relationship, we need to put a foreign key in one of these tables. So what would happen if we put the P number here? Okay. Well, what's this mean to us? Well, since an attribute can only have one value, that would mean the employee can only work on one project. Right? We've already said, though, that an employee can work on many projects. Okay? So it doesn't work putting the project number over here. Well, what about Social Security number? We could put that over here. But if we put that as a foreign key in the projects table, well, how many employees could now be working on that? Well, this Social Security number is only going to point to one employee, so that would be one employee. But we said we want many employees to be working on this. Okay? So that's why we have the works on table. It also captures hours. Okay? And you might hear these called associative entities or intersection entities, and there might be a few other names out there. I call them associative entities. So to create an associative entity, and this is going to be our works on table, the normal way to do this is take the primary key of both of the entities involved and make a composite key. So in the works on, we have ESSN and we have PNO. That's the composite key. Now, what do we do here? Okay, to implement that many-to-many? Well, with this being the primary key, we know that one works on entry can only refer to one employee, and it has to. It's a foreign key, so it has to refer to an employee. Okay? Well, we take this information here that said an employee could work on one-to-many projects, and we move it down here. We do a similar sort of thing for the project number. Since we have a PNO in this, we know it can relate to one and only one project. Okay? And we take the cardinality and participation here, and we move down here. So now we say a P number or a project can have one-to-many works on entries. We have the employee can have one-to-many works on entries. Okay? So we're getting what we originally wanted to be able to model, this many-to-many relationship. Okay? And any one of these entries in the works on table only refers to a single employee. Likewise, any entry here only refers to one project. So to implement this many-to-many relationship within a relational database, we need to use an associative entity like works on. Okay? So that's another thing with guideline 1. We want good semantics. We don't want multi-valued or composite attributes, and we need to make sure we have the entities necessary to implement a many-to-many relationship. Okay? So that's our first guideline. The second guideline, reduce redundant information. And I'm going to show a couple of slides from just the figures, some of the PowerPoint slides with the figures, because they'll help me demonstrate this a lot easier than me trying to draw a lot of things. Okay? But the second guideline, we want to reduce what we call anomalies associated with this. How do we get those anomalies? We get it by duplicating data. I think. So here's the layout of the schema for these tables, for these relations or entities. Okay? And we have functional dependencies in here. A good relation, the determinant, and we'll talk about more about functional dependencies in a bit, but the only determinant should be the primary key or an alternate key. In this case, we have the primary key determining other attributes, but we also have a non-prime attribute determining other attributes. This is how we can get some redundancy. Similarly, we have part of the primary key here determining some information, because the project number isn't necessary to determine the employee name. Likewise, the social security number isn't necessary to determine the project name or location. So we're going to get some redundancy, and this next slide shows what happens if we have a table with this information. Let me blow this up a little bit. So we can see here in the first one, where the department number is determining the name and manager SSN, we can see we've got quite a bit of duplication already. And this is a trivial table. We've only got 8 entries in it, I believe. Yep, there's 8 in there, I think. And, but we have research duplicated 4 times. What if we had 80 entries or 800 entries? Okay, these departments would probably have lots of duplication. I don't know about you all, but if I tried to type the same word the exact same way 100 times, I'm going to make some spelling errors. I'm just not going to type it correctly. I'm an okay typist, but I'm not perfect by any stretch. Likewise, I would have to type in the research department and the manager SSN for every single employee in any department. Okay? We have a lot of redundant information there. We don't want to have that. Similarly, in this other table, we have to start repeating employee names, repeating project names, project locations. And we could also have those sort of problems when we're inserting a new record. We could just plain old spell stuff wrong. If we delete, modification is very similar, okay? We could modify somebody in the administration department to the research department and make a mistake when we're entering either the department name or the manager SSN. Okay? So we don't want that to happen. Right? Deleting, all right, we can get some unintended consequences when we delete something. What if we deleted James Borg? We just deleted the headquarters department as well. Probably didn't want to do that. So if you delete a record, we want to get rid of that employee. We don't want to get rid of the department, but since the information is all put together, when we delete James, we also delete the headquarters department. And that's an anomaly that we don't want to occur either. We want that department to stay there. How do we fix that? We create tables like we have here. If I delete James now, poof, I just deleted James. I didn't delete the headquarters department. It's down in the department table, and it still exists. So we get a new boss. The new boss's name and information go here. We put the new boss's social security number here. We now have a new boss for the company. But if I delete James, I don't have that headquarters department anymore. Right? So we don't want those sort of anomalies to happen either. Right? And really the goal of what we're doing is we want to reduce this duplication and reduce the chance for these anomalies. With everything we're doing in this chapter, that's the whole goal. Reduce this sort of duplication we see so we don't have this sort of repeated data. Because when you have repeated data, you can get weird, you can get those anomalies because you can spell stuff wrong or type it in wrong. Right, the next guideline, let's take a look at what it says. It says reduce null values. Okay. Sometimes null values make sense. Other times you can have them in there and it takes up space. And really, if you see a null value, there's one of 3 things. Okay, it means that, okay, this just doesn't apply to that person. And if we look at our company database, okay, James does not have a supervisor. All right, James is the boss. I get that a boss doesn't have a supervisor. That kind of makes sense to me. However, when we come down here and look, James has charged null hours to Project 20. There I am wondering, what does this null mean? Does James actually has some hours to be charged, but we don't know what they are. Okay. Do we just not know? Do we not, right now I have no idea if James would charge any hours or not, so we don't know. We don't know if there's something to go there, or if we know James charged something, it's just unavailable to us not right now. Or does it just not apply? I don't know which one of those three reasons applies here for this record in this table. I just don't know. Okay, and that's the stuff that we want to avoid. Think about the employee table. Okay, we might have international workers working for us. In that case, we'd probably want to have an attribute that says visa status. Okay, but what if, only 15% of our employees are foreign workers? Only 15% would have a visa status. The rest would be null. That probably doesn't make sense to put that attribute in here. Okay, we would want to have another table possibly that would just have Social Security number and the visa status only for those employees that actually have a visa. That would make more sense. So we want to avoid these nulls. It just, can lead to problems. Also, if we come back here to the works on, what if I'm totaling hours for project 20? What do I do with that null value? Or if I'm counting the number of people who have charged hours, do I count James or not? Those are some questions that can lead to weird results if we don't know exactly why that null is there. Okay, so we want to avoid these null values. Right? And then we also want to disallow the possibility of generating these spurious tuples. And how do we do this? We make sure that we can join relations on a primary key foreign key relationship. There's an example in these figures, and I think this is it right here. Okay. We have these two relations. The only attribute they have in common is p location, and p location is not a primary key in either of the relations, which means it can't be a foreign key between these relations either. However, since it's the only attribute that is the same in both relations, what would happen if we joined on that? So here's the data in those two tables. If we join on Bel Air, we're going to get some weird results. Let's go see what it actually looks like. Here we go. So we did a natural join, which joined on that. Now, when we do this, look, we've got Social Security number. I believe that's John's Social Security number, but look how many people are listed with that Social Security number. Oof. Because we are joining on the project location. All right? And that these spurious tuples are the ones that plain old just doesn't make sense. Okay? So the ones you see with the stars here, this has all been generated because we joined on a bad join condition, on project location equal to project location. Not a good thing to do. All right? If you come up that you have tables that look like this, okay, you need to redo your tables because this plain old just doesn't make sense. Okay? And if we think about it, the employee name, that should not determine the project location. Okay, Social Security and project number, okay, determining hours is fine, but the Social Security number has nothing to do with determining the project name and project location, so they really even shouldn't be in this table. So we have two really poorly designed relations here, and because of that, that's why we had all of these anomalies that we see. Okay? And that's what we want to avoid. We don't want those anomalies in our data. Okay? And that wraps up these guidelines. Okay? Then we're going to start talking about how we actually normalize functional dependencies and then how we normalize our data now. Okay, now we're going to look at these functional dependencies, what they actually mean. And really, in essence, the functional dependency means that if you know the value of an attribute or attributes in a relation, that you can determine the rest of the values in that tuple. Okay, so if I know like a Social Security number, let's look at the employee table. If I know the social security number for an employee, it determines what the first name, middle initial, last name, birth date, and all these other attributes are. Okay? We say the social security number determines the rest of those attributes. Likewise in the department table, if I know the department table number, I can find out what the name of the department is, who the manager's social security number is, and when that manager started managing this department. Okay? So it functionally determines. Right? Let me write out this department table so you can see what I actually mean here. So for the department table, we have department, and within there we have D number, we have D name, D number, D name. I'm writing them out of order, but that's okay. It doesn't matter. Manager SSN and manager start date. Okay. The department number is the primary key. Now, I didn't write it in the same order that they have the table, but that's okay because the order of the attributes doesn't matter, right? But this is determines in what we call a well-formed relation. If it's in third normal form, the only determinant should be your primary key or any alternate keys you may have. So let's look at this first. How would I write this as a functional dependency? Okay. So I would say my first functional dependency in this table is D number. Okay. And then we use an arrow. And this arrow can be read as D number determines the department name, the manager SSN, and the manager start date. Okay. So if I know the department number, I can find this out because the department number determines those attributes. I can also say the department name is determined by the department number. So how to read it every other way. This value that is to the left of the arrow, that is known as the determinant. Okay? It's the determinant. It determines the other. Okay? If I were to do the works on table, okay? Works on has the ESSN, the PNO, and hours. Those are the primary key. The functional dependency in this relation is ESSN, PNO, determine hours. Okay. So if you have a combination of attributes that determine something, you put them on the left side of the arrow and you surround them in parentheses. And that is how we can, and this is what a composite key actually is. Our works on table is in third normal form, so the primary key is determining the other attribute in this relation. So those are what functional dependencies mean. Let me look at this slide here. Okay, neither of these tables are in 3NF. Okay. So for this one here, and I hope I can draw on this. I don't know. Let's see if it'll let me draw. I hope so. It's not letting me draw. But I would have two functional dependencies. The first one would be social security number determines e-name, b-date, address, d number. I would have a second one that would say FD2, d number determines d name and manager SSN. Right? So to read this, these pictures, these diagrams the author has in the book, the functional determinant is where the arrow starts, and where the arrow's in, those are the attributes being determined by that determinant. So we say the SSN determines the e-name, b-date, address, d number. D number determines d name, d manager SSN. Down in this table, we've got FD1 would be SSN and P number in parentheses on the left of the arrow, determine hours. This functional dependency, FD2, would be Social Security number determines employee name. Our functional dependency 3 would be P number determines P name, P location. Right? So neither of these tables are in third normal form. Right? This is why we had that redundancy that we saw earlier. This is why we don't want to have this. We want to reduce that redundancy and the chance for those anomalies. To do that, we need to make sure that the determinant in the table is only the primary key or possibly an alternate key. And what I mean by that is we look back here in the employee table, if we had an attribute called employee ID, okay, I would think we could all reasonably assume that an employee ID would identify an employee. Likewise, the Social Security number identifies the employee. Well, what we learned about, we have candidate keys, you got to pick one. So if we picked SSN, we still would have the employee ID here. The employee ID could still determine these other attributes. It's not a key, but that's okay because that's just the way the data fell out. The database administrator would probably make that alternate key indexed because there may be times when we need to go in by the employee ID as well as the Social Security number. So whichever one of those we didn't pick for the PK, we want to index as well because the primary keys are automatically indexed. And that indexing gives us faster access to the data. Okay, so that's what a functional dependency is. Right? Now we're going to move on to normalization. Okay, so what is normalization? All right. It's really a process. We analyze given schemas based on their functional dependencies and primary keys, and we want to achieve these properties. We want to minimize the redundancy of data and minimize the chance for those anomalies that we've talked about. Okay. As we normalize data, we want to make sure that we don't end up with something like we saw here, where we had, where the only thing we could join on is project location and get those spurious tuples. So we want to make sure we avoid that. Okay. We also want to make sure that any functional dependencies we have in the data remain. Okay, because when we get done with our normalization, we're going to be creating new relations and changing things and moving stuff around. We got to make sure that our functional dependencies are still intact. And having the functional dependencies still intact also means that you didn't lose any attributes when you did your normalization. Okay? So the book covers several types of normal forms. We are going to talk about first normal form, second normal form, and third normal form. Okay? There's a fourth and fifth normal forms. There's a Boyce-Codd and a domain key, I believe. The only time I've ever looked at those was in graduate school. Okay? Out in use in the real world, the production, we usually just stop there at third normal form. This does enough of minimizing the redundancy and minimizing the chance for these anomalies that most organizations just stop right there. And that's why I only cover these. If you go to graduate school, knock yourself out. You can learn about those other ones because they are interesting, but for me, they're just not practical to be implemented. Okay? So we're going to talk about first, second, and third normal form. Now, I would encourage you on Canvas, there is this normal forms handout. Go ahead, you might want to pause this and open this handout up because that's what I'm going to be speaking about, speaking to or from. Hopefully you have this handout up. So I'm going to talk now about the different normal forms. So we're going to start at first normal form. And really, if a relation meets all the requirements to be a relation, meaning it has a primary key, it doesn't have the multi-valued attributes, it doesn't have composite attributes, each attribute comes from a specific domain, then we're in first normal form. Okay? If we look at this first relation I have here, we actually have two composite attributes. we have name, because that could easily be broken up into first name, last name. Okay? So we do have a composite attribute there. And like I've spoken about, our company database has this. It has address. This, the one I have, includes the zip. So instead of having address as the attribute, I could have had street address, city, state, and zip. Okay? That would take care of that composite attribute there. So we don't want composite attributes in our first normal form relations. Okay? Likewise, we don't want multi-valued attributes. Okay? In this relation, we still have this composite attribute there. Would need to be split up into first name, last name. But we have this. Okay? This is a multi-valued attribute. The composite attribute, the different attributes we could break it up in come from different domains. Okay? With the address, okay, we have street address in there. That's not a city. A city's not a street address. A city's not a state. A zip code isn't any of the others. So we actually have 4, they're related but dissimilar types of attributes within this composite attribute. In a multi-valued attribute, that's more like an array. These are all course numbers, so we put course numbers into our multi-valued. We can't have that either. Right? How would we fix these? With the composite attributes, we just create more attributes, right, in the same relation. Okay, so composite attribute, we create a first name, last name, split it up accordingly. With these multi-valued attributes, we actually need another schema. So in this case, I'm assuming that our PK would be the student ID. So I would have another relation. I'd get rid of courses here, and I'd have a relation that had student ID and course. So for this student ID, 8896, they would have 4 different entries in this table. That's our table, or 8896. And then we would put the relevant course numbers in there. IT 351, IT 468, and then the others. Okay, the ADMG and RMT. So we would need a separate table to be to fix the problem of a multi-valued attribute. So those are 2 things. To be in first normal form, must meet 2 conditions. Okay, no composite attributes and no multi-valued attributes. So those 2 conditions must be met for a relation to be in first normal form. Now the problems I give you, all of the relations will be in first normal form. So let's go ahead now and talk about second normal form. Okay. With second normal form, there are 2 requirements that must be met. First, the relation must be in first normal form, and then we can't have a partial dependency. Okay. So let's look at see what it actually means by a partial dependency. A partial dependency is, so a partial dependency, okay, this is when a non-prime attribute. Okay. Now a prime attribute means that the attribute is part of the primary key. So SSN and P number are prime attributes. The non-prime attributes are the attributes that aren't part of the primary key. Okay. So our Z name, P location, those are non-prime attributes. So we have a partial dependency is when a non-prime attribute is determined by part of the primary key. Okay, so with FD1, that's a pretty awesome functional dependency. The entire primary key, okay, we've got SSN, we've got P number, determines ours. That's what we want, the entire primary key determining a non-prime attribute. If we look at FD2 though, now we have a problem here because it's only the social security number. Okay? Only the Social Security number is determining the employee name. So that's a partial dependency. We don't want one of those because we want our relations to be in second normal form. We want to be able to get from first to second. Likewise, project number. Part of the primary key is determining project name and project location. Okay? So what would we do here? How do we normalize the data from first normal form to second normal form? We have to create new relations. And if we look at this, okay, we've got FD1 is right here. SSN P number hours. Okay, we've got that. That's a good relation there. We don't have any partial dependencies. FD2, okay, is implemented here. It's Social Security number determine an employee name. Okay, that's a good relation as well. No partial dependencies. Okay, if we look at this relation, EP3, we have P number determining P name, P location. Again, this is a good relation. It's in second normal form because no attribute now is determined by part of the primary key. EP2's primary key is SSN, EP3's is P number. So when we do this, we want to make sure now, remember, we can't lose any functional dependencies. Well, if I FD1, that's here. FD2 is here. FD3 is right here. So we didn't lose functional dependencies. We have to make sure we still have all of our attributes. So I've got SSN P number, hours, yep. Employee name, yep. Project name, project location, yep. So we have all our attributes accounted for. We now have a set of relations that are in second normal form. Now, give you a little hint here. What does a relation have to have a partial dependency? I'll let you think on that for a second. Okay. In order to have a partial dependency, we must have a composite key. We have to have a key that is made up of two or more attributes, because if we don't have a composite key, we can't have a partial dependency because you can't take part of one attribute. Okay? If it's a composite key, we've got multiple attributes making up the primary key, so we can grab that. But if it's a single attribute primary key, you will not have any partial dependencies. So that means if the relation's in first normal form, it has a single attribute primary key, that relation is also in second normal form. There's nothing you need to do to it because you can't have a partial dependency. All right, and then I have another example here. Now we would need to split this one up into three relations too. Our first one would be FD1, it would be R1, and it would have the student ID as the PK, and then we've got F name and L name. Okay. Our second relation, R2, we can have student ID and course ID determining the term, sorry, not two, and the course ID, and we have the term in there. Okay. Student ID, course ID, primary key. Okay. If we have R3, that would be the course ID determining the course name. So we'd have the course ID, which would be the primary key with the course name. Okay. Now I'd need to check my functional dependencies. Do we have FD1? Student ID, can it determine first name, last name? Sure can in relation 1. Can student ID and the course ID determine term? Yep, I have all three of those attributes in R2. And then finally, can I implement FD3, where the course ID determines the course name? I can do that one too. So now I would have relations that are in second normal form. I need to evaluate them to make sure we still don't have any partial dependencies. Okay, R1 and R3 have a single attribute primary key. They can't have a partial dependency. If I look at R2, Well, I know from that functional dependency, the course ID and the student ID determine the term. I've got that with a term, and I'm good. Now I have taken this relation that was in first normal form, I've now put it into into second normal form. Next thing we're going to look at now is third normal form. Okay. Third normal form, for a relation to be in third normal form, it has to be in second normal form, and there can be no transitive dependencies. All right. A transitive dependency means that we have a non-prime attribute determines another non-prime attribute. So this employee-department relation, right, we have a transitive dependency here. The only prime attribute is SSN. Okay? But the SSN cannot determine the department name and the department manager SSN. Only the department number can. Okay? So if we know the department the employee is working in, we could determine the name and manager SSN. But we would be repeating department name and manager SSN in every single tuple of employees that are in the same department. We don't want that. We don't want the chance for those anomalies associated with the insertion, deletion, and modification. So how do we fix this? We create a separate relation. Right? We take what FD1, this would be FD1 here. Right? We can take that out. We can pull that functional dependency out, and it's right here. Social Security number determines those attributes. We take this functional dependency, which would be FD2, and we pull it out and put it here. Now notice that department number became a primary key. Okay? When we did this, it became a primary key. Okay? Because every relation must have a primary key. Now the determinant is, in this case, department number, which we now have as our primary key. It determines the department name and department manager SSN. These are really good relations right now. We don't have the chance for most of those anomalies. We might still be able to, I don't think, but then the chances for an insertion, modification, or deletion anomaly are reduced significantly. I don't even know how we would do one. So that's where we want to get to. And now, like for the second normal form, to have a partial dependency, you needed a composite key. For third normal form, in order to have a transitive dependency, what do you need? I'll give you a second to think on that. Okay. To have a transitive dependency, you need what? You need a non-prime attribute, so you got to have one non-prime attribute determining another non-prime attribute. So in order to have a transitive dependencies, you need two non-prime attributes. Doesn't mean you will have a transitive dependency, but you cannot have a transitive dependency unless the relation has two non-prime attributes. Okay. So that pretty much works as what the normalization is. Okay. Now, as you normalize your relations, there's some decomposition that I want you to use. So if you have your first normal form relation only has a partial dependency, then you should name the relations. You should put a number after them, R1, R2. And if there's no transitive dependencies, R1 and R2 just move over. Okay. And we're going to talk about abstraction here shortly, but we extract some of those relation names. Let's just come back up here and talk about it now. All right. Now, instead of writing all this out, I don't even really care when I'm doing this normalization what the names of the attributes are, or the relation for that matter. I could very easily have had R, A, B, C, D, B would have been underlined, E, F, G. Okay? So I could have that written. And then I would have down here A, B, C, D, E. That was a D. And over here I would have E, F, and G for my relations. I would have R1 here. I started with R. I have R1, R2. Okay. And this is how we will be doing the problems and on the assignments and in the practice soon to come, as well as on the tests. You will be given relations that just have a relation name R and then some attributes within them. Okay? And then you will need to decompose them appropriately. So if you have a relation named R, it has a certain number of attributes with it. It has a certain attribute that's the key. If R is listed over here, it needs to be exactly the same as the R that was there. So the R1 here needs to be exactly the same as the R1 there, okay, because you've named it. And if you want to go back to the words, if this was the employee table or the employee department table, well, it's still the employee department table. Over here, we'd have the employee table and the department table. Okay? So if a relation you name it R, it is R everywhere you use it. Okay? So let's look how we'll break it down. The first normal form only has a partial dependency. So we have to remove that partial dependency to get to second normal form. There's no transitive dependency, so what do? You just copy the information over into the third normal form. Okay? With a transitive dependency, well, there's no partial dependency, so your first normal form relation is also your second normal form relation. You don't have to do anything to it. Then, to remove the transitive dependency, we would split it out into R1 and R2. Okay? If your first normal form relation has both a partial and a transitive dependency, here's how I'd like you to break it down. We have the relation R to start with. We'll remove the partial dependencies and get R1 and R2. And now there could be an R3 and R4. Okay? I'm just stopping at R2 here. Likewise, over here could have been 1, 2, 3, 4. But I'm just splitting it into R1 and R2 in the example here. And R1 has the transitive dependency. So we have to decompose R1. And we do that by doing it R1A and R1B. Okay. And I will tell you, if you have R1 here and you do not have R1A and R1B over here, and R1 had the transitive dependencies, because I'll have students just list R1, 2, 3. You will not get any credit for the third normal form relations. Okay? I want you to show that you understand that you are decomposing R1 and you name it appropriately. And we'll go through some examples on this, and I think it'll help make this clear. Okay, now we're going to do a little bit of practice normalizing some relations. Before we do, I want to just recap the first, second, and third normal forms, and then discuss how we can abstract the attribute names into just single letters so we don't have to deal with such big names, because really we depend on the functional dependencies. Anyway, let's go ahead and take this table. This table is 14.1 out of the textbook. Right? For first normal form, the relation should have no multi-valued attributes or nested relations. You can think of it that way. They can't have composite attributes either. Right? If they do, this second column is how we fix it, the remedy for it. If we have multi-valued attributes or a nested relation, we form new relations. Okay, because we can't have them. The department locations table in our company database is an example of that. Okay? If we have composite attributes, we just keep them in the same relation. We just split them apart. Like address in the company table, we could have street address, city, and state. Okay? So that's for first normal form. Second normal form, okay, we can't have partial dependencies. Okay, we've got to have, it says where the primary key contains multiple attributes, so we have to have a composite key, and no non-key attribute should be dependent on just a part of the primary key. How do we fix it? We decompose the relation, we set up a new relation. Okay. Third relation, We can't have partial dependencies, a non-key attribute determining another non-key attribute. Okay? How do we fix that? We decompose it again and pull out that transitive relation, that transitive functional dependency, sorry. Okay? So that's just a quick recap. Right? Now let me talk about abstracting the names a bit. We've got a couple of relations here. Okay? Instead of going ahead and writing these out, because really when we're normalizing, all we care about is the functional dependencies. I could really care less what the names are when I'm doing this. So instead of using ename and all this, I could very easily just use A, B, C, D, E, F, and G. If I have the key, I underline the key appropriately. Okay. Down here for this relation, I could have A, B, C, D, E, F. And again, don't really care what the names are, it's the functional dependencies that I care about. Okay. So in the problems I'm going to work, I'm not going to use full attribute names. I'm just going to use an abstraction and just use letters. Now, I would never implement a table with just letters for the attribute names. That'd be silly. But to work us through and get us familiar how to normalize data, using this abstraction I think works fairly well. Okay. So let's go ahead and look at a few problems here. Okay. Here's the first one. Right? Notice I have some questions here. On your homework assignment, you'll have little check boxes. I'll also list all of the attributes, so it'll look something like this. B, C, we got D, E, and F. And each of these will have a checkbox beside it. Okay, because I'm going to want you to tell me, are the first and second normal form relations the same? Well, if I don't have a partial dependency, they will be. Are the second normal form and third normal form relations the same? If there's not a transitive dependency, they will be. And then you have to determine the attributes. And again, not an attribute, the determinant, sorry. Which attribute is the determinant? How can you tell what the determinant is? It's any attribute on the left of an arrow in any of the functional dependencies. It doesn't have to be a key. When we get to third normal form, it should be a key, either the primary or an alternate. But before we get there, doesn't have to be a key. And we can see that in some of these. Okay. Oh gosh, let's get rid of all those letters I put up there. Well, most of them anyway. Okay. We can notice D number is a determinant here. It's not a key. Here we have SSN for FD2 and P number as determinants, and neither one of them are the key. They're part of the key, but neither one are the key all on its own. Okay, we have to combine them. FD1 takes that into account. Okay. So those are questions you'll have to answer for each problem. Now, these two, I would wait until you get done normalizing this relation. Okay. The determinants we can tell right now. I've got A, B, C, I've got B, I've got C. So I'll just put a little check mark beside these. I have our little X, A, B, C. Those would be my determinants. Okay. So let's go ahead and normalize this now. Okay. If I look at FD2 and FD3, those look like they're partial dependencies. My primary key is A, B, and C. Okay. And then I have B determining E and C determining F. So both those are partial dependencies. Okay. And we'll have to remove them from our answer. So what am I going to get? Well, I'd like to go ahead and just do this. Copy the R over. And it looks like I'll have three relations. I can go ahead and number them now. And then I make sure I have the appropriate attributes in each. So I'm going to have A, B, C determining D. So I can do that right there. Okay. I've got B determining E. I can put that in a relation. Let's say determining, oop, I went too far. E, oop, I don't know what I hit there. E. Oh, I had the okay, let's try this again here. There, and then I can get rid of that. Okay. And then I have C determining F. So I can do that. And I'll take those away, and I have C and F. Okay, now I need to make sure I didn't lose any attributes. I had A, B, C, D, E, F. I've got A, B, C, D, B and E, C and F. Okay, good so far. Now, did I lose any functional dependencies? Okay, do I have a relation where A, B, C can determine D? I sure do. Do I have a relation where B can determine E? I do. Do I have a relation where C can determine F? I have that as well. Okay. Now, can any of these have a transitive dependency? And I can say no real quick. Why? Because they all have only one non-prime attribute. And you need two non-prime attributes to have a transitive dependency. So I can go ahead and do this, copy them over, and there's my answer. Right? Now I need to think, okay, did I have, well, we'll answer these questionnaires. That's what I'm talking about. Is the first normal form relation also in second normal form? So there's my first normal form relation, and it's obviously not in second normal form because I created three relations there. So I would put no, or I wouldn't check the box. That's what you'll do, just not check the box. Now, in my second normal form the same as the third normal form? Yep, sure is. Okay. So there's the answer to that problem. Okay. And it's the complete answer because, like I said on the homework, you'll be having to check boxes here. You won't actually put one for the N. Right? You'll only check the box for the yes. Right? You'll check the boxes for the determinants. You'll have to make sure you normalize from first to second, and then normalize second to third. And remember that hierarchy that I talked about earlier. Where'd it go? Do I still have it here? I may not have put it in here. Let me go find that hierarchy. Let's get it over here so we can see it. I'll just put it in down here somewhere. Or I could drag over my notes. That might be easier. Let me just drag over the notes here. That hierarchy is right up there. Okay. And remember what we're doing. All right. If we just had transitive or partial dependencies, this is how we would do it. R to R1 and R2. No transitive dependencies, R1 to R2. All right. So let's go ahead then and look at another problem. Okay, so we've got this problem. Okay, go ahead and pause the video. Try to work this on your own. Okay, and when you unpause it, I'll show you what the answer is, how we got there. So go ahead and pause the video. Alrighty, let's go ahead and take a look now. Let me get back down in the right place in my notes. Okay, so if I'm looking at this, do I have a partial dependency? Well, I don't think so, because A being the key, and I don't have either A or B as a determinant all on its own. So I don't have a partial dependency. So what would I do there? I would go ahead and check that box right away. Okay. There's no partial dependency, so the first normal form is also in second normal form. Okay. Now I need to check, do I have a transitive dependency? Kind of looks like I do. I've got C determining D and E, and C is a non-prime attribute. It's not underlined. So I'm going to have to remove that transitive dependency from R. So how do I do that? I go ahead and I'm going to just make two copies. Let's see if I can try that again. B. I don't know why it's not letting me paste here. Okay, this is really crazy. Let's make sure everything's... there it did. That was weird. Okay, so let's take and see what we have. So I need to have AB determining C. So I can go ahead and do this right there. AB determining C. Okay. Now I have to be able to have a relation where C determines E. I'll take away A and B. I've got C and D. Need to number these appropriate, decompose them appropriately, and C is also now a key. So looking at this, I think we're good. Right? Is the second normal form relation also in third normal form? Nope, so I won't check that box right there. I will have all five of my attributes here. I can get them in order. And which attributes are the determinants? Well, it is the attributes that are to the left of the arrows here. So we got A, B, and C. And I would check those boxes. Okay. So here we had a relation that just had a transitive dependency. The first normal form, since it's no transitive or no partial dependencies, it's also in second normal form. We have a transitive dependency, so we have to be able to pull that out. And when we do, that non-prime attribute that was the determinant now becomes a key. So let's go ahead and look at one more of these, and then we'll be done. Okay, so let's go ahead and look at this last problem. All right. We've got, again, A, B, C, D, and E. We've got FD2, FD1, and that should actually be FD3 there. All right. So first thing I can do is go ahead and look at the determinants. Okay, I've got A, B, and C on the left side of the arrows, so I can go ahead over here and just mark A, B, and C, checking those boxes. Now I need to evaluate, do I have a partial dependency? Okay. Well, it looks like FD2 is a partial dependency. And why? Because I have here B is the key, part of the key. A and B is the key, B is part of it, and B determines D. So that's a partial dependency. FD3, we have C determining E. That's a transitive dependency. So we got to leave that intact as we move to second normal form. Okay. So let's see what we'd have to do here. So I'm going to end up with a couple relations. So I'm going to copy this over. Okay. Now I have to have AB determine C and C determining E in the same relation. Okay? Because C determines E. I can't have E in another relation than C. It's got to be in the same relation. So if I look up here, I'll have AB determines C, got that, but then I got to have AB determines, or C determines E. Okay? So there I have a good one. This will be R1, this will be R2. And in R2, I'm simply going to have B determining D. So there's our second normal form relations, okay? We need to make sure R1, it's got a composite key. It doesn't have a partial dependency. Look, AB determines C, that's good. C determining E, that's good. So no partial dependency there. I can't have one in R2 because we only have a single attribute primary key, right? Now I have to deal with this transitive dependency, okay? And it's going to be taken care of up here in R1. So let me copy both of these over because R2 is not going to change, but R1, we're going to need to work on it. All right. So I have to be able to have AB determining C. All right, so I want to get E out of here because I left E there, I would have a transitive dependency. Okay, and then my final relation, and this would be R1A, this is going to be R1B. And I need to have C determining E. So I'll do that. Make sure I underline C since it's the key. We'll underline it. And then we can answer those questions up here. Well, first we'll check these. Okay, AB determines C. That's a good, because both A and B, the entire primary key, determines C. C determines E. That's fine. Couldn't have a partial or a transitive. Couldn't have a transitive up here because there's only a single attribute, there's only one non-prime attribute. And down here again, one non-prime attribute. So none of these could have a transitive relationship right now. So it looks like we're done. Now I have to answer my questions over here. Are the first normal form and second normal form relations the same? Nope, so I would not check the box. Are the second normal form and the third normal form the same? Nope, so I wouldn't check the box. So this would be my answer. Now the one thing I want to point out where some students make a mistake, they don't do this decomposition. If you simply had R1, R2, and R3, you would not get any credit for that. You need to decompose the relations appropriately. Okay? And that wraps up the practice here. Okay? So you can go ahead and look at the homework and get started on that. That's it.